Hello, everyone. Thank you for joining. My name is Itay Shakury. I'm the director of open source at Aqua Security. And I'm here today to talk to you about runtime security using a couple of very exciting technologies, eBPF and OPA. And I want to start this talk by actually sharing an example. This is a real example, actually, that our research team at Aqua has discovered. So this is a Docker image on Docker Hub that was doing something useful. You know, maybe you've even used it. And if you have used it, you probably scanned it, because this is what we do with container images. We scan them for vulnerabilities, for misconfigurations, for known malware, and so on. And if you would take that image and scan it with any popular static image scanner, it would be all green. All the tests would pass, and it would be seemingly innocent, except it won't, because it would try to do something bad once you ran it. And the reason is that there was a malicious binary hidden in the entry point. Now, this sounds very sophisticated and maybe challenging, but actually, if we take a look at the entry point, and you can see it right there, so you see this weird looking string here that you may recognize as a base64 encoded artifact. And you can see the following line, which basically decodes this string and then executes it. So it's a pretty simple, even disappointing kind of techniques to hide something, but it was extremely effective because it managed to evade pretty much every static image scanner due to the simple fact that this malicious image was not existent at the time that the container was scanned. It only kind of appeared at runtime after the code in the entry point was executed. And my point here is that static image scanning, when we discuss it in the context of container security, it's a staple of container security. It's something that we've been doing for a lot of time, and it's a really important practice that we have managed to adopt, but it has its blind spots. And by simply relying on that tools, we were also overlooking some entire categories of risks, actually, such as the one that I just demonstrated. Which brings me to discuss runtime security. So runtime security is kind of taking the opposite approach. Instead of shifting left, we're trying to shift right and to look at the workloads, at the containers while they run. And this is the conclusion that we reached earlier by discussing that example, that the only way to really know what the container is going to do at runtime is to run it, right? So this is what we're going to do. And when we run the containers in the production, what we're trying to do with this runtime security solution is to detect suspicious behavior at runtime. This is the goal that we're trying to achieve here. This is what the solution that I'm going to discuss today is going to help you achieve. And we have a project that is called Tracee. It's an open source, completely open source, no secrets there, completely free on GitHub. So if you go to github.com/aquasecurity/Tracee, you can see everything about Tracee, how it works, what it tries to detect, and how. And throughout this talk, I'm going to introduce you to this tool, and specifically how this tool leverages eBPF and OPA in order to achieve runtime security. Okay, so let's discuss runtime security architectures in general, even regardless of Tracee. Pretty much every runtime security solution will have the following architecture, where there are two components basically at play here. One is the monitoring part. This is the part that deals with monitoring everything that happens on the operating system, right? We are trying to protect our servers, our production probably. So we will install some component onto that servers that will have visibility into every single thing that happens. We want to capture as much information in as much detail as possible in order for us to make detections later on. So that part basically just produces raw data, a lot of events. And then we take those events, we take this raw data, and we feed it into the other component, which is the detection engine. This is a separate component that is looking into that stream of events, and it is trying to find patterns, suspicious patterns, based on predefined rules that we will give it. So there are rules that we ship with Tracee. You can write your own rules as well, but basically you give it something to look for. You kind of teach it what a suspicious pattern might look like, and then it looks for those patterns within the stream of incoming events. This is a very, 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 very high level overview of Tracee or a runtime security solution. And you know the title of the talk, so you know that there are two core technologies that play here. One, eBPF for monitoring the operating system. So eBPF is a very exciting Linux technology. It's part of Linux, part of the Linux kernel. And in a nutshell, it allows us to instrument the operating system and attach to very interesting points in the kernel workflow and actually execute our own code in there. So this is actually the uniqueness about eBPF, that it allows us to run our own code there so that we can collect whatever information we might need, and we can do it in a very safe and reliable and performant way so that you will not be affected by this overhead. I'll talk a little bit more about eBPF soon. And the other technology that is helping us build Tracee is the Open Policy Agent, or for short, OPA. OPA is a graduated CNCF project that deals with policies and policy enforcement. It was meant for scenarios like authentication, authorizations, so you can define the rules, the policies that you want to enforce, and OPA gives you the language, first of all, to describe those policies, and then the tool to enforce them. Another popular scenario that we see OPA at play is with Kubernetes, for example, as an admission controller. So it will receive all of the user requests to create resources in Kubernetes, and you can define policies of what kind of things you want to allow or to deny, and OPA can help you enforce that. We use OPA slightly in a slight creative way, because we think that the incoming events, we see them as input documents, and we express OPA policies to help us look for the specific patterns that we want to look within those events. And we will also talk more about OPA and see an example for that later in the talk. All right, so what we're going to do next is to zoom into each one of those components and see them at play. Let's start with the first one about monitoring, the monitoring component. And to discuss that, we first need to understand this mental model of how the operating system works and what it means, basically, operating system tracing. So this is a very common common diagram where you have your application, it's running on the computer. There is hardware to the computer, right? And your application is trying to make use of it. Let's say it's trying to create a file, or it's trying to communicate over the network, or whatever it needs to do with the computer. Actually, the hardware itself is inaccessible to the application directly. In every modern operating system, including Linux, the kernel, which is the component of the operating system that is in charge of managing the hardware, is the only component that can actually touch the hardware. So the kernel is the only way that we can touch the hardware. How can we do something simple like open a file? Because the file exists on disk, we need to interact with the disk somehow. So the way, the mechanism that operating systems lets us communicate with the hardware is via system calls. System call is a common interface where the kernel exposes these system calls. Basically, think of them like functions that you can call from the outside. And by calling a system call, let's say the open system call, which is a real system call in Linux, you can ask the kernel to open a file for you. So let's go through these layers from the top to the bottom. You, the application developer, or someone who uses an off-the-shelf application. The application is trying to open a file. Probably the coder, whether it's written in any language, Node.js, Python, C, it doesn't really matter, is going to use some library that will call into another library that will call into a lower level library, which will eventually call a system call. And that system call will be handled by the kernel. The kernel has access to the hardware, and via probably some device driver will actually move the needle, read the bytes, and return the result to you. And the reason that I'm sharing this at this moment is to show you exactly where eBPF fits in. eBPF lets us plug right there between the system call and the kernel. And this is the perfect place for us to be if we want visibility into everything that happens on the computer. Because it doesn't really matter whether the application is written in whatever language, whether it's running in a container or in a VM, or whether it's privileged or not. None of it matters. All of the code that is being executed on the computer and is trying to access the hardware is going to eventually go through us, thanks to eBPF. And this is where we have the opportunity to examine what's going on. But more than that, unlike other instrumentation technologies that lets you just log the calls, in this case, we can actually run our own code at that point. And our code, by the way, runs in the kernel. So we have a lot of visibility into everything that happens at that point. We can collect additional information. Sorry, collect additional information and provide a lot of contextual information around the raw event. And this is what helps us create very high quality events with accuracy and reliability. And the result of this is that the eBPF probe, this thing that we send into the kernel to help us collect the data, will tell us, yeah, an open system call was detected here, and this is all of the information that I can extract at this point. All right, so this is operating system tracing that we can achieve using eBPF. We discussed system calls. There are a lot of system calls in Linux. And the good news is that Tracee allows you to trace pretty much all of them out of the box today. I counted it just before this call, just before this talk. It was 353 system calls that we support in Tracee. It's a lot. It gives you everything, all of the information that you may need in order to make quality detections later on. But the interesting part is that on top of those system calls, Tracee also gives you access to other kernel events. These are specific points within the kernel that we chose to instrument manually in order to give you more information that is more meaningful in a security context, because this is where we are at. We're trying to detect suspicious behavior. So those other kernel events, which I will demonstrate in a second, will give you access to more reliable information, more accurate information, and more secure information. And we keep adding more events to Tracee every day. Probably by the next time you'll see this recording, the numbers will be different. But what I want to do next is to demonstrate what Tracee eBPF looks like. By the way, in the Tracee code base, we actually keep it that way, that the monitoring part is separate from the detection part. So we call the monitoring part Tracee eBPF. And yeah, and now we can see it in action. All right, so I moved over to my terminal here. And Tracee eBPF is now an executable, is a command that you can run. And I can tell it, first of all, to just list all of the events that it can trace. So what you see here is a huge list of all of the system calls and other kernel events that we can trace in Tracee. And for each one of them, you can see what kind of information you can expect to receive from this event. Let's start Tracee with no arguments, which will start a general purpose trace. It will just try to trace everything that happens. And you can see already that things are happening here. Maybe try to open a file here and you can see more things are happening. Let's stop the trace. And just in a couple of seconds, we captured almost 150 events. And this is because, you know, it's a Linux machine, it's alive, it's doing things all the time. And we can see a glimpse into what we were able to capture here, at what time, what user, what was the command, process IDs, what is the exact event, and the arguments of that system call. For example, we can see an open system call. Open@ is a variant of open. And you can see all of the arguments that were given to this system call. And you can use this information to do very interesting investigations. Let's do something else. Let's ask Tracee to trace just the open@ system call. If we do that, oh, sorry, I forgot to add an event. I want to ask Tracee to trace events of type open@. And now we see slightly reduced output, still quite verbose, but slightly reduced. Actually, let's add another filter here. Let's ask Tracee to only show us the output of the cat command. All right. And I'm doing a cat down here for a file, and you can see now a more digestible output. These are all the open@ events that happened from this cat command. You can see it trying to open some files, eventually also opening the test file that I asked it to open. And this is a good opportunity to also mention the other events that we add on top of system calls. Open@ is a system call. And you can see here that you get access to the real information that was given to the system call. In this case, test, just the name of the file. But there are many different ways to access a file in Linux, to reference a file. So for example, you can say the relative path, the full path, you can give it a DRFD that changes the way that the path name is handled. You can give it a file descriptor that is already opened. This is Linux, so there's a lot of flexibility. But what I can do here to make the output more usable is to add the security file open event. This is an event that Tracee is introducing on top of the open system call. And I want to show you the differences. This is the open@ system call, same one that we've seen earlier, that shows us the output of the tests, the opening of the test file. And this is the security file open that gives us the resolved file path to the real file that was opened. So this is much more usable for us if we want to make some kind of assertions on this output in order to make detections. Moreover, this event, the reason it's called security is that it is more secure. I won't go into that. We've written a very detailed blog post about that in the Aqua blog, but system calls, because they sit in the border between the user and the operating system, the user has some influence on what they pass to these calls, what kind of arguments and when, and it is vulnerable to some kind of attacks, while the security events, which generally called in Linux LSM functions, are not. So it's not only more usable, it's also more secure to use this kind of events. I could also ask Tracee to output to format the output as a JSON, and I could pipe this JSON stream into other tool that will, look into, for example, the args. You see here the args property, and we can look at the second argument here, and you can further play with it and create your own kind of detection logic. But we'll see that there's a much better way to do that soon. All right. So that was a quick segue just to show you what the raw data looks like, the monitoring part of the runtime security solution of Tracee. Let's move on to discuss the second component, the detection component, the detection engine, like we call it. So we're now zoomed in to the detection part. We have on the left events flowing in from Tracee eBPF. This is raw data, as we've seen. And on the right, we will produce detections. These are alerts, actionable alerts that the user can process. So we've seen an example of how an event looks like. I'm just formatting it here as JSON document, so it's easier to reason about. And we have access to all of this information. We just need to know what to look for. So this is where we are using the Open Policy Engine. More precisely, more accurately, the Open Policy Agent, the language that you write policies in is called Rego. So technically, our rule engine is able to process Rego signatures. This is how we call them, Rego signatures. And it looks something like this. So we ship Tracee with a bunch of Rego signatures for you. You can also write your own. You just create a new text file. It looks something like this. And let me just bring the pointer back. You create a text file. You can declare some metadata for prettier output, but the interesting part is this block here. You create a rule that is called Tracee_match. And within this rule, you just give us a list of conditions that needs to be matched in order for this signature to detect. So think of it like a big if-else statement where you are only required to provide what's inside of the if. What are the conditions that you are interested in? And you have access to the input here. So you can say things like input.event name. This is the name of the event. So input.event name, let's see if it equals to openet. This is the system call that we're interested in. And then let's see if the input has an args field, which it does, and it's an array. So let's just run through all of the elements in this array and look at the one called value. Look at the field called value of every one of those elements. And let's call this file path because we know this is what it represents. And then let's see if this file path equals to etc shadow, which is a very well-known file that you don't want to manipulate with too much. If you do see this file being manipulated without your knowledge, then it's probably malicious. So this is a very simple detection that will detect that. But what I want to show you here is really the simplicity of writing a new rule or a new signature for Tracee. And it all really thanks to OPA, thanks to Rego. Writing something like this in code would probably result in, I don't know, 50 lines of code that with a lot of loops and a lot of checks and a lot of stuff there. Here it's just 3 lines. You know, we just assert that the event name is OpenNet. We just implicitly iterate and look into the elements and then do another assertion, and that's it. Pretty neat, I think. Yeah, and what I want to show you now is example for signatures that we have in Tracee. So I'm going to move over to my browser here. And this is Tracee on GitHub, Aqua Security/Tracee. All the code for the eBPF part, the monitoring part, and the rules part is here. I'm going to click into the rules part and signatures, Rego. And you can see a few Rego signatures here. We keep adding more and more. And let's look into, for example, this signature. I chose this one because this one is maybe the most complicated one that we have, but it's still pretty simple. So it's really demonstrates the readability and expressiveness of this signatures language. So it's a text file. You declare some metadata here just so that the UI can show you something helpful. You tell us what kind of events you are interested in subscribing to. And this is the boilerplate. And then you can see these Tracee match blocks. There are 3 here because this is a code injection signature, as you can see here. And what it is looking for is indications that someone or something tried to manipulate a running process at runtime. And there are different ways, different techniques to do that in Linux, right? Our research team has researched and investigated the different ways that someone might be able to manipulate a running process's image at runtime. And it came up with these 3 ways. So they just wrote them down, codified them as Rego code. The first one is using the ptrace system call. So we see if the event name is ptrace. We look at the argument called request, and you can see here a slightly different way to do that. We also provide helper functions, Rego helper functions. So you can ask something like, give me just the value of the request argument without writing that more verbose code that you've seen earlier. You get the result and you see whether the ptrace request is ptrace poke text. Poke text means that someone tried to manipulate the code of that program. If it did, then it's clearly a code injection behavior. And there are other behaviors here. Let's see a more complicated one. In this case, we're interested in the security file open event. And we want to see if the opened file looks something like this. This is a regular expression. So if the file being opened is /proc/pid/mem, which is a special file handle that Linux offers to manipulate the memory image. And we also check whether it was opened for write and not for read. And if so, it's a detection. Here we can see another cool thing, not only other helpful functions and so on, we also see that you can also return a result from the detection. It's not just a true false. Yes, there was a detection. You can also give us some evidence of, give the user some evidence into what really happened. And, you know, there are many different ways, so we're not going to cover all of the signatures. Just wanted to show you a real world signature that is one of the more complicated ones, but I think it's actually pretty readable and approachable. Okay, moving back to the slides, we have covered the monitoring part, we have covered the detection part, and now let's zoom out and review the solution end-to-end. We have the operating system, which we now instrument using Tracee's eBPF probe. This is the probe that we send into the kernel to report back to us about everything that happens. It reports it back to Tracee eBPF, which is the component that is in charge of monitoring. Tracee eBPF is then continuously generating an endless stream of events that represents everything that happens on the operating system. And this raw data is being fed into the Tracee-Rules engine. This is the rule engine, which is loaded with Rego policies, Rego signatures. Each one of those signatures is always looking for a suspicious pattern. And if one of the signature has found that pattern, it will create an alert. The alert that the detection itself is human readable, is actionable, unlike the very verbose raw data. This is something that you should understand and you should be able to respond to. And you can also ask Tracee to send this event to you in whatever preferred way you have for communication. So you can ask Tracee to send a message over a Slack channel, send you an email, open a Jira ticket, whatever, using a very flexible webhook interface. And this is how the runtime security looks like end-to-end in Tracee. And just to finish that demonstration, I wanted to show you that in action. Actually, I'm going to move over to our documentation very quickly, which is linked to from the GitHub repository. And I'm just going to copy this line over here. This is the quick start example of how to run a Tracee altogether. So this Docker container, aquasec/Tracee, includes Tracee eBPF and Tracee-Rules and all of the signatures that we ship with Tracee, and it is set up so that it it sets everything up so that you immediately start monitoring and detecting things. Let's just run it like this, and you can see that it has loaded some signatures. And actually, what I want to do now is to execute this test file, and you can see that Tracee has detected something. This is a standard input-output over socket, which means that Tracee has detected that someone has redirected the input or output of some process into a remote endpoint. And it even gives you the remote endpoint that we detected and what was the command, what was the container name, and so on. So this is something that you can actually understand and react to and hopefully mitigate. All right, great. So I hope that you learned about runtime security today. I invite you to go over to github.com/aquasecurity/Tracee. We have discussions over at GitHub. So if you are trying out Tracee, you have a question, you have a suggestion, you just want to reach out and say something, please go to our discussions area and start the discussion. We'll be happy to talk with you and try out Tracee. Give us a star and tell us what you think. If you want to get in touch with me personally, you can find me over Twitter at Itay, Itaysk. And with that, I want to thank you. I hope you enjoyed this talk, and I hope you enjoyed the rest of the conference. Thank you.